Okay, welcome all. So today to another lecture. So this will be on a circular column. Previously we have studied the rectangular column axially loaded. So this will be our circular column. It will be also axially loaded. Here the main thing will be the load carrying capacity will be changed. Okay. So as we all know, the load carrying capacity of circular column is more than the rectangular column, and also here the lateral ties or the transverse reinforcement will be changed. Here it is known as helical ties. Okay, so we will see how to design it. So let's start. In this video we will study the steps uh, involved in designing a circular column. In our next video we will solve a numerical. Okay, so let's start. So step 1 will be step 1. Step 1 is check for short column. We have to check it is a short column or a long column. Okay, check for short column. So how we check for a short column? Mainly by using the slenderness ratio. Okay, so the what is slenderness ratio? The slenderness ratio is L effective divided by LLD, least lateral dimension, should be less than 12. Okay, so this will be a short column if this satisfies. So one thing we can tell that for a circular column, the number of bars for a circular column, the number of bars, minimum number of bars should be provided. For rectangular it was minimum was 4 bars. For circular column it the minimum bar is 6. 1 2 3 4 5 6 6 bars. 6 bar is minimum. Okay, we have to provide it. So we will see now the step 2. Step 2, let's see what is the step 2. Step 2 is calculation of minimum eccentricity. Calculation of minimum eccentricity. Let's see, the previous formula is same only. E minimum we have to calculate. E minimum formula is unsupported length. Okay, L unsupported divided by 500 plus least lateral dimension divided by 30. Okay, or 20 mm, or 20 mm. Okay, 20 mm, whichever is maximum. Okay, now we again know that we have to check. So see here, in previously in rectangular column there was two direction x and y, but in circular column there, see, in circular column there will be only one direction. There are no two dimensions. See, the diameter, the dia of the circular column will be same. See here, this dia also same. If you measure it from here, this dia is same. If you measure it from here, this dia is also same. So the dia is same everywhere. So E minimum will be calculated in one dimension only. Same, the check for minimum eccentricity. Okay, minimum eccentricity. So what is the check? We previously know that E minimum should be less than or equal to 0.05 LLD. Here for circular column, LLD is equal to dia. Okay, for circular column. Okay, so we will see now the next step. So the next step will be calculation of the longitudinal reinforcement or the load carrying capacity. Okay, so step 3 will be calculation of load carrying capacity. Load carrying capacity, that is mainly represented by pu. Okay, pu. So here is one note, that is, in case of circular column it is 5% more than the rectangular column. For circular column, load carrying capacity carrying capacity is 5% more than rectangular column. Okay, so now the main thing comes here, we have to change the formula. That is, we know that the previous formula was 0.4 fck AC, area of concrete, plus 0.67 Fy AS, area of steel. So 5% more. So 5% more means 1.05. So to multiply it with 1.05. Okay. Yeah. So this is the formula for the circular column load carrying capacity. Here see, here AC is area of concrete. Okay. So how can we change it? So AG, gross area, is equal to AC plus AS, area of steel. Okay. So here AG is equal to the area formula of a circular, pi by 4 d square, means we are taking it as dg square. Dg, what is dg? Dg is the gross diameter. Okay, so dg, see here, this diameter only we are taking it as dg. Okay, this diameter only, the gross diameter. Okay, so now what will be the formula? See, AC is equal to pi by 4 dg square minus AS. So this will be the AC formula. Okay. Now the next step will be the calculation of the number of bars. Okay. Step 4 will be you have to assume a dia of bar for the longitudinal reinforcement. Okay, longitudinal reinforcement. Then we have to calculate the number of bars. Number of bar will be the total area of steel with what we have got divided by the area of one diameter steel. Okay, so we will get the number of bar. Okay, so then what we have to check? Then we have to check for the maximum and minimum reinforcement area. Okay, so now what we have to do? We have to check for minimum and maximum reinforcement. Okay, so what we know, the AS should be greater than or is equal to 0.8% of cross section area, and the AS, area of steel, should be less than or equal to 6% of the cross section area. Okay, so this we have learned previously also. Now the main catch come here in designing the transverse reinforcement or the helical reinforcement. Okay, so the step 5 will be the transverse reinforcement. Okay, the helical ties. Helical ties. Okay, so let's see how we will start it. So we know, as per IS 456, as per IS 456, the main formula comes here is 0.36 FCK by Fy, multiply it by Ag divided by AC minus 1, that should be less than is equal to VH divided by Vc. So let's see what are this. So here we can Vc is equal to the volume of core. So that can be found out by AC into 1. Okay, so the AC is the area of the core, so we will see what is the core, and the VH, okay, the volume of the helix, can be found out by pi by 4. Phi h square means the helical dia of the helical, that square, into 1000 divided by p. Here p is the pitch and pi dh. Okay, so this is the formula. Here mainly we have to find out the p. Here mainly we have to find out this p from this formula, that is the pitch. Mainly pitch is the spacing. Okay, in circular column it is told as pitch, the spacing. Okay, so one thing we will see here, how to find this uh, phi h dh. Okay, so we will first draw a diagram. Okay, let's see. We will first draw a circle. Okay, now we will draw. Okay, wait, give me a minute. Okay, we'll draw another. Okay, so now we will see what are the things. Okay, so dia of the helix, so here you can see here a dh. So dh is the dia of the helical portion. Okay, dia of helical portion. So this will be the dh. This thing is the helix. Okay, so from this middle of this to middle of this will be the dh. Okay, so this part is the nominal cover. Okay, so this part is the nominal cover. Okay, so we will see there is one thing also, that is dc. Okay, dia of the core, dc. So how we will find out the dia of the core? See, there is also one thing, that is, if from this part, from this outer helix to this outer, okay, from this outer part to this outer part, it is known as dc. So dia of the core, dc, is equal to dia of core. Okay, so we will now draw the reinforcement also, so it will be easy for you to understood. Okay, so we have drawn the reinforcement also. Okay, so the gross dia, that is we have previously told it as dg. So the dg will be, if we take from this part and from this part, so this will be the dg, gross dia. Okay, this part will be the gross dia. Okay, so one thing, dg will be the gross dia. Okay, so we will now see dg. So dg will be given only, so we will see how to find the dh and the dc. So see, if we find out the dc is, we have to only from dg we have to subtract this nominal cover from this side and also from this side the nominal cover. So dg minus 2 nominal cover. Okay, nominal cover. So this is dc. Now we will find out the dh. How to find out the dh? See, so dh is from here and here. So from dg we have to subtract 2 times the nominal cover, and we have to subtract the 2 times the half of the dia of the helix. Okay, so this is the dia of the helix. Okay, so this thing we have got, so you can write it here also. Phi h is the dia of helix, helical tie. Okay, see one thing we can tell, that if this is a circular column, and these are the longitudinal bars. Okay, so the helix will be the, or the ties will be in this shape. Okay, this is the helical tie. So now this we are calculating. Okay, so one thing, if you could not get this formula, how it is coming, so we will see how this formula is coming. Okay, this formula, let's say this formula is coming from, see, let's say from this part to this part is the spacing. Okay, this is the pitch. Okay, so volume, see, this is the volume of the helix. So the volume of the helix, that is VH, represented by VH, is equal to area of the helix into length of the helix, that is area of helix into the length of the helix, so see, now the area of the helix, so the area of the helix will be simple, pi by 4 into the diameter square of the helix. So this is the area. The length, what will be the length of helix? So here you have to just see one thing, that is number of the rings. See, the length will be number of the rings, the number of these rings coming. Okay, into the length of the one ring, into length of one ring. How we can find the length of one ring of a circular thing? That is the perimeter. Okay, that is the perimeter. So see, number of rings. So number of rings, how we can find? We are mainly, if you remember previously also, we calculate everything in 1 meter. So 1000 divided by the pitch. So if we divide the total area with the spacing, so we will get the number of rings. So these are only, so total area is 1000 and the spacing of one ring is p. So we are doing it for the calculation of number of rings into length. So perimeter is 2 pi r. So see here, 2 pi r. If we 2 r we can write it as also diameter, so pi d. So pi into diameter of the helix. Okay, so this thing is coming from here. Okay, so now see the volume of the helix. What is area into length? So this is the area and this is the length, so we'll multiply it. So VH is equal to, see, pi by 4 phi h square into 1000 into p into phi dh. So this is the formula coming. Okay, so this is the formula coming. See here, the same thing we have written it earlier also. See, so from here, our aim is to calculate the pitch. From aim, sorry, aim is to calculate p, the pitch. Okay, one thing is only left, that is we have to check for the pitch. Check for pitch. So what will be? See here, the pitch should be greater than is equal to 3 times the diameter of the helical bar, or 25 mm, and the maximum is p should be less than or equal to dc, that dc by 6 or 75 mm. So what is dc? Dc is the dia of core. Okay, so we have seen it, how we will get this dc. Okay, so dc we have seen here. So this is the design step. We will, in our next lecture we will do a numerical based on this. Thank you.